Okay, well, welcome back, everyone. Our reef pulling our reef situation is as follows. I just thought we'd review the formation of hemiacetals. This compound here is a good model actually for simple sugars. It basically looks like any of these simple aldoses or ketoses. I've just sort of stripped away all of the other OH groups. And the mechanism for forming a hemiacetal is something we went over in chapter 19. Recall that we get protonation of our carbonyl oxygen, just as we so often do. Once that's accomplished, we're well set up for this OH group to attack and form a new ring. And so this is how you can get either either 5-membered or 6-membered rings. After that, of course, we just need to pull off that proton with a water molecule. And I think you'll see this whole process is acid catalyzed. So here, for instance, I'm borrowing a proton from you guys, and then a couple steps later, I'm giving you that proton right back. And of course, the blue bond here is the new one. So I just thought that was worth reviewing since it's relevant, as I said, both to the material from the previous class and to today's material. But we're just taking attendance today, so there's no consequences otherwise. So I have information on exam 3. I still want to analyze the data. I think there will be some small curve, maybe something in the 5 to 10 points range, but the average was pretty similar to last time. So I'll look over that and I'll let you guys know as soon as I post, or rather when I post official exam 3 scores, which will hopefully be over the next couple of days. I'm kind of not at home at the moment, but once I do that, it will tell you with your official score that will include any curve. So basically, today we just need to finish up the chapter on carbohydrates, and I basically want to cover glycoside formation since we've covered all of the other reactions of simple sugars, if you will. I also want to spend a bit of time on disaccharides and how to draw them and how they're formed. And then last but not least, there's 2 processes that I want to make sure we cover that are used a lot in the industry, at least so I'm told. I'm not a carbohydrate chemist, that involve manipulation of carbohydrates, by which we can either extend the carbohydrate chain by 1 carbon or elongate the chain, if you will, or we can do the opposite. We can also chop off a carbon. So first of all, in terms of glycosides, as I said, we covered all of these other reactions, exhaustive alkylation, exhaustive acylation. We did all the redox reactions of simple sugars. One that I wanted to save for today was the formation of what we call glycosides, which is the reaction of simple monosaccharides, generally with an acid catalyst in alcohol solution. And that can be ethanol or methanol. It's generally going to be some small alcohol like that. But in any case, there's a mechanism for that process, since we really covered that also in chapter 19, but there's a mechanism for that process that's in your book. And the mechanism in your book is not wrong. I think it's completely acceptable. Let me show you another mechanism that's acceptable. And this is the kind of reaction that I really feel probably has at least 2, if not 3 or 4 possible pathways. And I'm sure in solution, all of these pathways happen. The mechanism that I put here in your class notes is consistent with the mechanism that we learned back in chapter 19. And so if you were to take this sugar, which I believe, by the way, is galactose as opposed to glucose, I say that because the OH in carbon 4 is axial instead of equatorial. And that's one of the possibly 1 or 2 other D-aldohexoses besides glucose that I have memorized. I don't expect you to memorize any of them except glucose, but since galactose comes up so often, I happen to have committed it to memory. But let's say we took whatever the sugar is, again, I think it's galactose, but whatever it might be, and we heated it in methanol with a little bit of an acid catalyst. So we added a few drops of sulfuric acid. Well, and again, I'm using methanol just as an example. We could use any small alcohol and the mechanism would be exactly the same. So one way this might happen is by protonation of this anomeric OH group. We've seen that type of thing a lot. Once that's done, we can lose water as a leaving group. By the way, I'm sort of cheating a little bit here. This compound really isn't chair-shaped any longer. As soon as you introduce a double bond into a six-membered ring, then the ring flattens out and becomes more boat-shaped. But be that as it may, once that's accomplished, then a methanol molecule can attack, or whatever the alcohol is, can attack from below or from above. And the way you'll know which to do is by looking at the structure of the product that you're given. Here, the new methoxy group is below. I guess since it's pointing down, that's going to be the alpha anomer, isn't it? Right. So we show our alcohol coming from below. If instead this were the beta anomer, then we'd show the alcohol coming from above. So the way you know which to show is based on whichever product you're given. But once that's happened, we get the protonated species here, and all we need is another alcohol molecule, since that's all that's left, remember. Yes, we do get one molecule of water, but that's, as I'm fond of saying, going to be drowning in an ocean of alcohol. And so it's a non-factor. It doesn't make sense to use a water molecule if it's outnumbered by maybe, I don't know, 10 to the 15th power, 10 to the 20th power of methanol molecules for every one molecule of water. It doesn't make sense to use a water molecule in the mechanism. So we use the solvent to pull off our proton over here and get the glycoside, in this case, the methyl glycoside. So that's another perfectly acceptable mechanism. But I think the one in the book is just fine also. And I wouldn't be shocked if we could come up with one or two other plausible mechanisms. And I would further not be shocked if all of those happen in solution. So, but like I said, we've already gone over all of these reactions, the sodium borohydride to give the alditol, formation of aldonic or aldaric acids. We've gone over all of that. Good. So let me just make sure that I haven't missed anything before we go on to disaccharides. I don't think so. But the great thing is, once we understand the process of forming a simple glycoside such as this, glycoside meaning a compound of this type, once we understand that process, then we've got everything we need to know in order to understand the formation of disaccharides and even polysaccharides. And so that's all the information we need to understand the formation of some important disaccharides. Include things like lactose, which someone in the previous class said, "Don't at me," since I had, she was just kidding around, but since I had spoken about people who are lactose intolerant, which is of course not rare in its various forms, though interesting, I've read that lactose intolerance is rarer here in the US than in most countries on Earth. So that's kind of interesting. And there are some students gave me some interesting ideas they've heard as to why that is. And it's all very interesting. It's certainly not my area of expertise, but it's very interesting. In any case, lactose is an example of a disaccharide, and I think we also looked at maltose. Not that I really care if you memorize any particular disaccharide structures, but a lot of these disaccharides are things you'll have heard of. And if you understand how to make a methyl glycoside, then you understand how a disaccharide is formed. And by extension, if you understand that, then you've got everything you need to know in order to understand formation of a polysaccharide. So this would be your starch, this would be your glycogen. What about cellulose? You know, things like this. These are pretty important molecules that find their place in living systems. So in any case, with that being said, I think we're ready to consider disaccharides. So I just wanted to show you a few examples and how we draw them. So one example of a disaccharide is maltose. And I don't say that this is the only way to describe the structure, to write out the structure. It's sort of one of the ways I do it, but I don't say that's the best or only way to do it. But essentially, maltose consists of two glucose molecules connected by an alpha-1,4 linkage. So this means that the first glucose molecule is in the alpha form, and then we connect carbon 1 of the first glucose to carbon 4 of the second glucose. And incidentally, as I think I said, I sure don't care if you memorize that that's what maltose is, but I just thought you might find that interesting to know, that it just so happens that that's what maltose is. But certainly, I would never say draw maltose or draw lactose, or I would never do that to you guys. So I would say if we were going to draw maltose, we'd want to start by drawing our first glucose. So here you go. And you're going to be, I'm flexing again, I suppose. I drew both of these sugar molecules with one mouse click. I have them in a pull-down menu here. So here's our first glucose molecule, and you can see that all of the non-hydrogen groups and carbons 2 through 5 are all equatorial, which is that interesting coincidence that we had the other day. And I don't know why that is, but it sure worked out nicely. So notice that I then drew that first glucose in the alpha anomer, meaning that the oxygen is pointing down, right? The vowels and consonants don't go together, so alpha is down, beta is up. So this oxygen here used to be the oxygen, actually that's a lie. That oxygen there actually comes from the second glucose molecule. But this bond to that oxygen used to be to the OH on that first one. So there's going to be a loss of water, just as there was a loss of water here when we replaced that OH with a methoxy group. So same thing here, except instead of OCH3, you've got O, the rest of this whole big molecule. So, but it's exactly the same conceptually. So that's why that bond is pointing down. That's reflecting that it's an alpha linkage. And then this bond over here is the new one. That's going from carbon 1 of the first glucose to carbon 4 of the second glucose. Actually, I should label these as well. Here we've got carbon 1 of the second glucose. Here's carbon 2, carbon 3 over here, carbon 4 over here, 5, and 6. Actually, let me move the 4 so that it's a little easier to see what's going on. There we go. That's quite a bit clearer. And then carbon 6 is over here. That's the one bearing that, the last OH group. So, but that's how you would draw, maltose, which again is an example of a disaccharide. I again don't expect you to memorize the structures of any particular disaccharides. And were I to ask you to draw a disaccharide on the next exam, I would just as likely come up with one that doesn't even exist naturally, or if it did exist naturally, it would be a coincidence. But this at least gives you an idea. And we're going to do one more example of these, don't worry. But this gives you an idea of the process to follow in order to come up with the structure of a simple disaccharide. And my feeling is if you can draw a disaccharide, then you can draw a trisaccharide, and you could draw a tetrasaccharide. I don't feel like using up all your time drawing saccharide after saccharide after saccharide, but I think at the same time it's helpful to understand what the structure is of these things, because again, if you're going on in biochemistry, I don't think they're going to explain this sort of thing very much. And if you're not going on in biochemistry, I don't think it will kill you to have some understanding as someone who's going on in science. of, you know, what structurally makes molecules like lactose and even sucrose tick. Good. So again, if there's any questions on these things as we go on, please don't hesitate to bring them up. The other one I thought I would show you is lactose, which is, again, a frenemy of a lot of you, and I'm not trying to add any of you in particular. Jeez. I saw that and I panicked. I'm like, what? I didn't add anyone. I didn't mention anyone's name. But she was just joking around. Good. So lactose is actually a disaccharide involving galactose and glucose. And here, I would, of course, if you needed to use galactose in one of these things, I would tell you how it differs from glucose. Here I've shown in red how galactose differs from glucose. Notice that this OH group is axial rather than equatorial. And once again, this blue bond over here is our new bond that formed from the glucose molecule to the galactose molecule. Notice that it's in the beta configuration, which means that bond points up rather than down. And over here is your glucose molecule. And here we're connecting carbon 1 of the galactose to carbon 4 of the glucose. I should mention it's only a coincidence that both of these have linkages from carbon 1 of the first sugar to carbon 4 of the second sugar. Not all disaccharides have 1,4 linkages. They could just as easily be 1,2 or 1,3 or 1,6, I guess, since the oxygen in carbon 5 is taken up in forming the hemiacetal. So they don't have to be 1,4 linkages. But nonetheless, there's another example of a disaccharide. This is really going very much faster, as it usually does, compared to the first class, since I had all these structures drawn already. Maybe let me at least take a couple minutes to number all of these carbons. So that's carbon 1 of the first ring, carbon 2, carbon 3, carbon 4, 5, and 6. And likewise over here, you've got carbon 1, which I put carbon 1, I guess, in the alpha anomer. Is there a difference between beta and alpha sugars? In terms of reactivity, no. They're going to be in equilibrium with one another. But if you mean, is there a difference between beta and alpha linkages here, and can you get to a different compound? Absolutely you can. I think you'll find that if you compare, don't quote me on this since I can't claim to be an expert in carbohydrates, but I think you'll find that's how you get the difference between glycogen and cellulose. I think one involves alpha linkages and one involves beta linkages. But certainly do double check me on that, because I don't want to be leading you astray there. That's carbon 4, 5, and 6. Good. And again, of course, I would never expect you guys to memorize that kind of thing. You know, what's the difference between cellulose and glycogen or something like that. Now, in your biochem classes, when you get there, you may very well have the pleasure of memorizing differences like that. But I certainly would never expect you guys to memorize something like that here. I don't think that's appropriate for our class. It is appropriate for biochem, not so much for us. Good. So, but my whole point to all this being, if you understand how to form a methyl or ethyl glycoside, like over here, then we're doing the exact same thing when we're forming lactose or maltose. Not maltose. Yes, maltose. It's the very same thing, except instead of adding a small alcohol, we're using the OH group of another sugar molecule. But conceptually, they're exactly the same. Good. And again, if there's any other questions as we go on, please don't hesitate. I wouldn't be surprised if at this rate we end a little bit early. I can always go back and maybe, let's see. We had before this done chapter 23, I guess. We can always do, oh, I don't know, a chapter 23 reaction or something like that. Good. So, so much for this particular page. I do have another page all set up. The other things that I wanted to be sure to, wait a minute, was this, can you explain why the CO bond is equatorial again? Let's see. Why the CO bond is equatorial again, that's because it says beta over here. And beta doesn't mean equatorial, beta means up. And so that's why I'm drawing an arrow from beta to that bond. Because the blue bond is the beta bond, just like the blue bond is alpha over here. So I've tried my best to indicate over here with arrows to show what's going on. But do you see the difference between alpha pointing down and beta pointing up? No, that's it's no perfectly good question. I'm glad you asked that, but that it's confusing because alpha and beta has only to do with up versus down as opposed to axial versus equatorial. But good question though. Oh, any other questions then about either of these disaccharides? Hopefully that gives you an idea as to what to practice. So let's again go to our next slide. So as I was going to say, the other things I really wanted to go over were the so-called Kiliani-Fischer synthesis and Wohl degradation. And these are processes that we can carry out on simple sugar molecules that are easiest to understand when we consider sugars in the straight chain form. And really, I think the sugar needs to be in the straight chain form in order for either of these processes to happen. Granted, any straight chain form of any sugar is going to be present in aqueous solution in only a few %, but that's okay. The sugar can go into that form, and then we can go through either of these processes. So these are called the Kiliani-Fischer synthesis and the Wohl degradation, which respectively result in extending the carbon chain by one carbon or shortening the carbon chain by one carbon. And happily, since we're at that point, being pretty much at the end of the term, there's not going to be anything here I can show you that's entirely different. All of the reactions involved here are ones that we've seen before. So in the Kiliani-Fischer synthesis, I'm just showing here the top of the first carbon, and this could be in any sugar. So there could be 3, 4, 5, 6, 7 other carbons, however many. Doesn't really matter because all of these actions are going to occur on that first carbon. So the idea behind the Kiliani-Fischer synthesis is the first thing we're going to do is treat our sugar molecule with HCN. And that's a reaction we talked about in chapter 19. We're going to form the cyanohydrin. So if you've forgotten about cyanohydrin formation or the mechanism of that reaction, please go back and review that. That's in chapter 19. And we will get actually a mixture of 2 cyanohydrins. So we can have H on the left and OH on the right, or the opposite, and you'll get a mixture. You'll get both. That's why I'm using wiggly bonds over here. Once we have our cyanohydrin, we can reduce the nitrile with catalytic hydrogenation, and that will reduce it to the imine. So we're going from a triple bond to a double bond by catalytic hydrogenation. And we're familiar with catalytic hydrogenation. We understand that's a reduction reaction. And then, once we've done that, now we're going to play a trick on the system and simply hydrolyze the imine to give us the aldehyde. And so the nitrogen in the imine will wind up in a molecule of ammonia and thus wind up in aqueous waste. And so you'll see, if you look carefully, what we've done is we've extended the sugar by 1 carbon. And yes, you will get both diastereomers over here. So generally, happily, diastereomers are pretty easy to separate since, like I said, they're not enantiomers, they're diastereomers. So they will have different properties. Would you have to draw the bond squiggle like that? Could you draw just both that it make? Well, that will depend on how the question's phrased. You might be able to draw just one of them, but remember also in mechanism problems that it generally gives you the product that you need to aim for. So all issues of how do we know what to draw it's going to be given in the question. But as always, be careful with OWL. OWL might want you to draw both of them. OWL might want you to draw just one of them. But I understand the interest in knowing what you're going to have to put in answer to the exam question in order to get credit. But you've had 3 of my exams at this point. I think I make that pretty clear, what you will need to draw, which is the added carbon. The added carbon was in HCN, so that is a carbon in it. And by this process, we wind up converting that nitrile to an aldehyde carbon. So I would say that one's the added carbon. Maybe we'll color that guy blue. So that one is the added carbon. It had been the nitrile carbon in HCN. Good. So, but the reaction process is otherwise very general, and you can apply that to pretty much any sugar. It doesn't matter how many carbons are left down here, those are all just along for the ride, whether it's 2, 3, or 4 carbons or however many. All of the action takes place on the aldehyde carbon. And what used to be the aldehyde carbon actually winds up over, trying to select that carbon. There we go. So that carbon there used to be the aldehyde carbon. So that's the Kiliani-Fischer synthesis. And it's again quite general. And by the way, you could then go do the very same thing again. Since we've got another aldehyde carbon, you could go ahead and add HCN and add the second carbon. So you can do this arbitrarily many times. And if necessary, each time separate the diastereomers one from another. So much for the Kiliani-Fischer synthesis. In the Wohl degradation, we're going to do the opposite. We're going to shorten the chain by 1 carbon. And so here I'm showing the top 2 carbons in any given sugar. You will know what you need to show based on how the question's phrased, but I'm just doing this to show you that it's quite general. So the first step involves a reaction again on that aldehyde carbon. We're going to treat that with hydroxylamine, which is a reaction that we went over in chapter 19 to give a special kind of imine that's known as an oxime. And so the remainder of the elements wind up in a molecule of water, and we go from C double bond O to C double bond N. And so we've converted the aldehyde to an oxime, which I don't even really care if you know that this type of molecule is called an oxime. It's a special kind of imine. But once we've made that, we can now treat the oxime with a powerful dehydrating agent. And I think you can see here that we've got the elements of water, H and OH. And there is multiple good dehydrating agents. We talked about some of them in chapter 21. Acetic anhydride is certainly one of them. That's a very good dehydrating agent. Other good dehydrating agents include phosphorus oxychloride, or thionyl chloride is another very good dehydrating agent. As always, you're going to want to use the mildest one that will work. I would be kind of afraid to go straight to a phosphorus oxychloride. That's a really, really nasty reagent. Then again, acetic anhydride is nasty enough, but my sense is that's going to be milder, and so you'll want to use the mildest one that will work. We'll remove the elements of water and go to a nitrile. And once we've done that, presto, we can just do the reverse of formation of a cyanohydrin by treating this with some base. The mechanism is the same as the one we talked about earlier of cyanohydrin formation, except that it's run in reverse. And so what our methoxide ion is going to do is first pull off the proton on this alcohol functional group to get O-, and then that will kick out a cyanide ion and go back to the aldehyde functional group. And in so doing, as you'll notice, wipe out any stereochemistry. So it doesn't even matter that this is a mixture of the two diastereomers, because once you lose your cyanide ion, then that carbon is no longer chiral, so stereochemistry is not an issue. Good. So again, the reaction is otherwise very general. And in principle, you could then chew up the thing again and do the very same thing to this carbon and lose another carbon. So you could do that again arbitrarily how many times until you get back down, I guess, to glyceraldehyde. But otherwise, the reaction is quite general. You'll know what you have to put based on how the question's phrased. That's always going to be the answer to every question like that. You'll know what you have to write based on how the question is phrased. I think, at least I try my best. God knows I'm not perfect, but I do try my best to make that clear. Good, and this is embarrassing, but we have over 10 minutes left. That means in principle, we could review some things. I'm trying to think what came before this. Am I right that before this we did chapter 23, which was on aldols? I feel like that, why do I feel like we've done that already? Why am I blanking out? What am I forgetting here? Wait a minute, hold on. Why should I guess? I have it right here. Yes, of course it was chapter 23 that we just did. I'm losing my mind. NMR, that's true. Aldols, NMR, I forgot about NMR. Yep. We could do that if you guys want to go in a little adventure for a few minutes and go look at that website and look at some proton NMR spectra. We could surely do that. Since you guys were saying that aldol reactions largely made sense, it was just that the owl people are evil, but we knew already that they were evil. Would that be good? Should we go to that website and look up some proton NMR spectra? Or actually, we could do that. Hey, I like that idea, if I do say so myself. Let me make a new window. Let's do that. And then if any of those spectra are ugly, we can estimate them in ChemDraw. Since I'm not hearing any complaints on that, first I have to find that website. Where is it? Here it is, AIST. How could I forget about it anymore? Whoops. So let's see. Shall we start with maybe some 5-carbon compounds? I don't know. What about C5H12O2? That's not a name, that's a formula. C5H12O2. See if we find anything interesting. 2-isopropoxyethanol. That's kind of neat. Ooh. So there's your structure. Yeah, I'm liking that. So it looks to me, we're lucky the 2 methyls didn't wind up being diastereotopic. So it looks to me like we've got 1, 2, 3, 4 types of hydrogen. Looks like in the ratio of 2 to 2 to 1 to 6. And I think we're definitely seeing that. We've got these 2 types of hydrogen are kind of running into each other. This one would have to be the OH group, at least I think. Let's make sure about that. D is 2.57, yep. And then remember how we had an isopropyl group before where the 6H resonance was split into a doublet by the adjacent 1 hydrogen. This is a little bit messy over here. Let me see what happens when we estimate that on ChemDraw. So what was it again? 2-isopropoxyethanol. Let's see what we can do. Let me first of all, just so that I don't get confused with all of the windows. 2-isopropoxyethanol. I think that's right, isn't it? HOCH2CH2O isopropoxy. HOCH2CH2O isopropyl, rather. All right, you ready? Predict proton NMR shifts. It looks a little better. Isn't that interesting? Now they're saying that the OH group is out at 5.4 or something like that, which again, at a different concentration, it might very well be. But I think you'll see, other than that, they're actually pretty similar, aren't they? Yeah. So the only difference is where the OH shows up, which, as I told you, they can be almost anywhere. I always identify everything else first. So it's unfortunate, again, this area is complicated because you have two or more sets of hydrogens. Why isn't the OH proton split by the two H's in the adjacent carbon? Well, we said OH protons are very frequently not split. Sometimes they are, but they usually are not. And the reason for that is because OH protons undergo very rapid physical exchange in solution in terms of literally hopping from one molecule onto another. So they're very often not split. It's pretty common for them just to be a broad resonance like that. So that part's not surprising. Over here, unfortunately, maybe I didn't pick the best example, but we have, again, 2 or 3 types of hydrogen sort of falling on top of each other. But what the one part that's really nice is the 6 hydrogen doublet. That part makes sense. And again, at least as far as it goes, I think those two, yeah, I think this did pretty well, even in terms of chemical shifts. Yeah, I think ChemDraw did a pretty good job at predicting this spectrum. So let me see if I can find something a little bit less ugly. Trouble is, I really do need to go back to the, it just doesn't ever let you go back. I've got to start over and accept the disclaimer and all that. Which, that's their perfect right. Maybe I'll try to find one with only 1 oxygen. Maybe that'll be a little bit less ugly. Butyl methyl ether, methyl propyl ether. Hoping for something a little bit more complicated than that. Well, wait a minute, that one was pretty good. Oh. What about this one? I don't want to do an alcohol. Let's see what we can find in terms of, how about 2-methyl? No, that's going to be pretty boring. Sec-butyl methyl ether doesn't have the proton spectrum. All right, let's try adding a carbon and see what we get. C6H14O. Hexyl alcohol, it's going to be boring. 2-ethoxy 2-methyl propane. That sounds good. Maybe not. Oh, it's a tert-butyl group. Not only that, it falls right on top of one of the CH2s. Okay, that one's crappy. I'd like to do one that isn't an alcohol. Diisopropyl ether we already did. 1-ethoxybutane, they don't have the proton NMR. All right. What if we did, how about C5H11Cl? 1-chloro-3-methylbutane. S plus 1-chloro-2-methylbutane. Wow. Let me try opening it in a new window and see if that works out better. Ooh. Let's see. Looks like we once again have an isopropyl group. These really aren't separating out quite as much as I would like. Again, it looks like these protons are falling on top of one another, even though they're different from one another. They turn out to be so similar that they fall on top of one another in a heap over here. This CH2 would be split into a triplet, and that's exactly what we see. Meanwhile, once again, these 6 hydrogens are going to be split into a doublet, but it looks like, I wonder if ChemDraw is going to be able to do a better job there. Let's see. So what have we got again? 1-chloro-3-methylbutane. I like that one because at least it's achiral, and so we don't have to worry about diastereotopic protons or anything. But I'm surprised it came out that bad. Let's see if ChemDraw can do any better. And then that's probably a good place to end. That's a little better, isn't it? Now we're able to separate out these two. See, that's what I meant. You see how here's your CH in the isopropyl, that's 1.62, and here is 1.49. That's an example of, in principle, we could have as many as, let's see, there's 2 adjacent protons here and 1 adjacent proton over here. So instead of saying 2 plus 1 is 3, 3 plus 1 is 4, we could in principle have this split that into a triplet, and then this split each of those triplet lines into a doublet. You could have as many as 6 lines. As it turns out, we can't really see all of them. But here's our isopropyl group. There's our 6 protons that are split into a doublet by this proton, and likewise, that proton is split into 7 lines over here. You can maybe almost see all of them. And then last but not least, unsurprisingly, this one at 3.68, that's going to be the triplet that's split by the adjacent 2 protons. 2 plus 1 is 3. That all makes sense. I wonder how well it did on the chemical shift. It's saying 3.68. Not too bad. This is about 3.55, 3.6, something like that. It's not bad. But yeah, that's interesting. Once again, ChemDraw is doing much better than the experimental one. So they aren't always very high resolution here. And with that, just like that, I've run out of time. So that's the sort of thing you can find out by looking on that website. You might very well be able to get onto chemistry department computers and find ChemDraw on there. I thought that at least the department had a site license. But other than that, hopefully I'll be able to pick up my car today without any further incident. And then, as I said, I should be at home sometime tomorrow. At least that's the plan. So other than that, have a great day, and I will see you, have a great weekend, and I will see you all on Monday.